Okay, let's focus. Get out calculators. This is unit 13, our last official unit. Hopefully you downloaded the calendar and or your in-class problems already to get started. Basically what we're looking at electrochemistry, the important part about this whole business is the calculation of something called E naught and then E. This is cell potential, also known as electromotive force, EMF, and the units on this are volts. So when you buy a battery, it has a certain number of volts. You guys have already done this, I believe, in physics. Finally, they did something before we did. What are the units on a volt? You should know this. Joules? No. Joules per coulomb. Okay? Basically, it's a push, an energy per unit of charge. You're going to see later in the unit when we study that a coulomb, we're going to look at basically not one electron. We look at how many electrons do you think? A mole of electrons. So that's what we're going to focus on. And you're going to eventually learn how many coulombs there are per mole of electrons. And we'll talk about that later. But what I want to just focus on today is the fact that to figure out a total cell potential, we need two half reactions. We know that when something loses electrons, something gains electrons. What was that called? Loss and gain of electrons. We had a term for it. Starts with an R. Redox, reduction, and oxidation. So this is a paired system. We've got two half reactions involved. We're going to look at a table, and the table is going to be all reduction potentials, and we're going to figure out overall voltages. This little knot right here is standard conditions, and just like thermo, 1 atm, how many degrees Celsius? 25 degrees Celsius. And another thing we're throwing in there is the concentration of the solutions in these standard batteries all have to be 1 molar. All right? So we're going to focus more on this. But in order to kind of prepare for this, we have to review how to balance half reactions. Because again, we have an oxidation half reaction and a reduction half reaction that we need to look at. So these are the rules for balancing redox. We've already done it this year. We did it like in Unit 2 or something. So we're going to revisit it pretty quickly, though, because, again, this is big-time review. We're balancing in an acidic solution, so that means we're just going to balance it following the steps. We'll have H plus at the end. We'll be done. We don't have to do that additional step since it's not basic. But the first thing you want to do is identify what two things are changing oxidation number. What two elements? Give me one of them. Manganese. So let's take out everything that has manganese in it. As a kind of a review, what's the oxidation state change of manganese? It's going from a plus what to a plus what? Perfect. +7 to a +2. That's going down in charge. So this is a reduction half reaction. So let's go ahead and balance this half reaction before we do the other one. So starting with that first rule, it was balance everything but H's and O's. Is that done? Yes. Balance O's using water. How many what side? 4 to the right. Balance H using H pluses. How many what side? Okay, now we're going to balance charge. The overall charge on the left is +7. The overall charge on the right is +2. I'm going to add electrons once to one side to make them the same. Correct. 5 electrons on the left. Now that's a balanced half reaction. And if you know the term, there's a couple things people use. Leo the lion goes grrr. Losing electrons oxidation, gaining electrons reduction. This is gaining electrons. We already said that that's a reduction half reaction. Okay? The other one, which I don't like as much anymore because it doesn't say electrons. People get confused and think it's charged. But oil rig, oxidation is losing electrons. Reduction is gaining electrons. Okay? Either one of those is fine. Now, moving on, what other element is changing oxidation state? Carbon. Good. So we've got the oxalic acid going to carbon dioxide. Students mess this one up a lot because they forget to balance everything but H's and O's first. So what does that do? You need a 2 there. Now we're going to balance O's, and if you notice, it's balanced. So now we're going to balance H with H pluses. How many what side? 2 on the right. How do I balance charge? 2 electrons on the right. Okay, in order to add these up, I have to have a common number of electrons, so I'm going to have to multiply each by a different number. What am I going to multiply the top by? 2. So I'm going to multiply everything in this top equation by 2 to get 10 electrons. 16, 2, 2, and 8. What do I multiply the bottom by? 5, because we want the same number of electrons. Okay. Now I'm going to add these up, but now that you kind of know what's going on here, I want to clean house before I add up because that's less stuff I have to write. What always cancels? Electrons. So these go away. All right, in this particular case, there's only one other thing that can be cleaned, something that shows up on both sides. What is that? Yeah, the H+. We've got 10 and 16. What do I do? Get rid of 10 of them. So if I get rid of these 10, it leaves me with 6 H+. And I think that's it. So now I'm going to have 6H plus 2 MnO4- plus 5 oxalic acids gives me 2Mn plus 2 plus 8 H2O plus 10 CO2. And I would spot check, pick a couple things to double check and make sure they balance so you know you did it right. MNs, notice you have 2 MNs, 2 NMs. Check the charge. You've got a +4 overall on this side. You have a +4 overall on that side. If you do a little spot checking like that, you'll see that it is balanced. The problem says inacidic. Are we inacidic? Yeah, so we're done. Good? Y'all remember this? Okay, let's fly through the next one then. All right. Balance the following, but notice what's different this time. It's in basic, so we're going to have to add an additional step. First thing I want to do is pick 2 things that are changing charge. What's one of them? The bromine. So I've got bromate going to bromide. Balance everything but H's and O's. Done. Balance O's using water. How many what side? Balance H using H+. How many what side? All right, my overall charge on the left is a +5. This is a -1. So what do I need? Correct. If I add 6 electrons, I'm just left with these negatives, right? Because the 6 gets rid of those. So that's balanced. Okay, what's the other half reaction? This one's an easy one. Iron 2 going to, this is going to be a typical kind of electrochem reaction where it's literally just the charge that's changing, so you only have to add electrons. But you're still, people think it's a different process. It's still the same process. Balance everything but H's and O's. Done. Balance O's. Done. Balance H+ is done. Now we balance charge, so it's 1 electron there. In order to add these up, we have to multiply by a common factor, 6. So we just multiply this one by 6 because the other one will then cancel. That makes these electrons go away. Is there anything else we can clean house with? No, nothing else we can cancel on both sides. So I'm going to write this. Okay, so that is a balanced half reaction, but we're not done. Not a half reaction, sorry, balanced full equation, but we're not done because it's acidic right now. So to make it basic, who remembers what we need to do? Add, not waters, Add enough OHs to both sides to tie up those H+. So we're going to add 6 OH-, but whatever we do to one side, we have to do to the other. That is what makes it basic there, because what happens here is we make what? We end up with 6 waters. But the only bad thing now is we have to clean house again because we have waters on both sides. Can't have that. How many am I going to get rid of? 3. So I get rid of all these waters, leaving me with 3 waters on this side. So my final equation is 3 waters plus a bromate plus iron plus 2, 6 of them, gives me a bromide plus 6 iron plus 3s plus 6. The only reason I put that in parentheses is people think it's 60 H- instead of 6 OH-. So, all right, good? All right, so now let's take all of this and apply it. What I want you to look at first, This I've kind of talked about at the beginning. The only thing I want to add to it is the concept of voltage being positive or negative. When you go to the grocery store and you want to buy a 9-volt battery, do you want a 9-volt or a negative 9-volt? Yeah, 9-volt. In order for you to have an actual flow, you got to have a positive voltage or a positive E or E naught. E versus E naught. E naught is standard conditions. E is non-standard. You're going to learn that. We're going to talk about how to get from E naught to E tomorrow. If E naught is positive, the reaction is spontaneous, or what was the term now we're using? Thermodynamically favored. So if we want something to happen in electrochem world, we want an E to be positive, or it won't. If our E is not positive, we're going to have to plug it into the wall, outlet, socket to get some flow or something in order to make it go. All right? So let's go ahead and just look at some scenarios here. We're going to do these next 2 slides, but after this is the place you're going to go and refer to a lot. This is your reduction potential table. This is a table that is going to be very, very important that you get to know and love. Notice how all the half reactions are reduction. Electrons are being gained in every single one of those. There is such a thing as an oxidation table. I've seen them, but that's not what they use. They're going to use these reduction tables. They are listed in order, unfortunately, a voltage, not alphabet, so it's hard to find stuff. But one thing that you know is that the bigger the E, the more inclined it is to be reduced. How do you remember that? Look at the name of the table. It's a reduction potential table. The higher the reduction potential, so these guys are going to want to be reduced more than those guys. Okay? The higher the reduction potential, the more apt something is to be reduced. All right? So what we're going to do when we're doing full reactions, we're going to take a reduction reaction from this table, and then we're going to take another reduction but flip it and make it oxidation and change the sign. So that's what this is all about. So let's look at the first problem. It says, which of the following species is the strongest oxidizing agent? The good news is that agents have been removed from the AP exam. Instead of saying oxidizing agent, I want you to cross that out and say which is the strong, or let's cross out strongest too, which is the species most apt to be reduced, or most inclined to be reduced. So if I'm looking for the one that's most apt to be reduced, which is going to tell me about the potentials, which one is going to be the one? The one with the greatest. So what we're going to have to do, we're going to split this up, and I'm going to give different rows a different one to look for. We're going to have to find 3 reduction potentials and figure out which one's the highest. So the first 2 rows, I want you guys to find MnO4- on that table. These 2 rows, I want you all to look up Br2. And these last 2, I want you all to look up Ca+2. And just holler them out when you get them, exactly from the table. (1.51). Those of you who are looking for MnO4-, find it, now that you know the number. Minus what? 2.84. And Br2? (1.065). Okay, so kind of find those numbers, and so you can see what those reactions look like. You need to kind of get used to locating them on that table. All right, so which of the following is most apt to be reduced? Which is your strongest oxidizing agent? Most apt to be reduced. Which one? Yep, the permanganate, because it has the largest reduction potential. That's it. Okay? This is where we actually get into the whole concept of spontaneity or thermodynamically favored. Will aluminum displace copper +2 if I have a solution of copper 2 nitrate? This is actually a pretty important concept in chemistry. For instance, if I were to store my copper 2 nitrate in an aluminum container, if this is true and it happens, would this be a good thing to do, to store my copper if aluminum will displace the copper? No, what's going to happen? It's going to spring a leak, right? The aluminum is going to turn into something else. So you can also look at it as some people use scupulas to stir their mixtures. Well, scupulas that y'all have are usually made of a lot of aluminum. Well, if we mix a copper too, will that eventually displace the solution? Will that scupula get dissolved or whatever? So this has an actual application. In order to do this, we need to figure out whether the E of the whole reaction is positive or not. So we need to figure out an overall reaction and then the half reactions that are involved. Just looking at the English, aluminum displacing copper plus 2. Write that down in an equation. How would I write that? Aluminum. Al. Since it's a solid, we leave it at 0. Displacing copper plus 2. Don't worry about this copper nitrate. That nitrate's a spectator. But do you see how the copper in that nitrate is copper 2? So that's what this is. So if the aluminum were to displace and boot out the copper, what would it make? Copper, 0. And what would happen to the aluminum? It would go in solution and make Al plus 3. And that is the overall reaction. The question is, will that happen? So what we need to know is if the E of that is positive or negative. So what we're going to have to do is write 2 half reactions. And to do that, you just do the balancing that you already know how to do. Which one do you want to do first? Copper. So copper plus 2 going to copper. How do I balance that? Add 2 electrons. Let's do the other half reaction. Aluminum going to aluminum plus 3. How do I balance that? Add 3 electrons to the right. So there are my 2 half reactions. What I need to do is find the voltages on the table. Notice the first one, copper 2 to 0, that's reduction. You're going to find this on the table exactly as it is. So go ahead and look for it. I know this one by heart for some reason. I don't know why. It's 0.34. Okay. Now, what do you think we do with the aluminum? Because it's not going to be like it is on the table. It's going to be reversed, right? So we're just going to find aluminum 3 going to 0 and then change the sign. So what is aluminum 3 to 0 on the table as is? Negative 1.676, but because it was oxidation, we're going to make it positive. When I add these 2 up, I'm not looking for an exact voltage in this problem. They just want to know, will it happen? Is that a positive or a negative when I add it? Positive. Therefore, this is thermodynamically favored, and it will happen. So I do not want to store my copper 2 in an aluminum can. Got it? All right, let's do another one. Practice just like this. Will magnesium displace tin 2? What do I write? Mg plus Sm plus 2. And what do I make? This boots out the single replacement Sn and... Okay, I meant to finish this before I moved on. Go back up here for a second. If we wanted to write an overall balanced equation, that's a pretty important thing, and we need to do it. So what would we do? We'd multiply the top by 3 and the bottom by 2, right? Kind of get used to doing this in one step, because this would be an easy one to just write 3Cu plus 2 aluminum. Do you see I'm doing it, multiplying and writing it again at the same time? But there's something I want to address. Is something bothering you about me multiplying through? What? Well, they canceled, so I just didn't write them down. That didn't bother any of you with my voltage? Yeah, that's the question. You actually don't. A lot of students will go ahead when they balance, multiply the voltage through by whatever they multiplied the equation through, and you don't. And what that has to do with is your definition of voltage. A volt is a push per unit of charge. Okay, so let's say I push Peter down the stairs. Okay, I have a certain voltage, a certain push per Peter. If you were to multiply me by 4, that would mean there'd be 4 demos pushing 4 Peters down the stairs. Does my push per Peter change? No. By definition, this is push per unit. So we do not multiply. It's not like thermo where we multiply the delta H by the new number of moles of the equation, okay? So don't do that. I tend to add these up first before I ever go over there and start balancing the equation, so I don't get into the habit. All right? Okay, so now that we know that, let's go ahead and find our half reactions. We've got magnesium going to Mg plus 2. This is oxidation. And I balance that, and I've got tin plus 2 electrons going to tin. That one's the reduction. Be really careful here because there's a tin 4 to 2, a tin 4 to 0, and a tin 2 to 0. We want the tin 2 to 0. So go ahead and look for that one as is. Since that's the reduction, I like to do that one first. That's going to be as is on the table. Positive or negative? It's negative on the table. Because it's oxidation, we're going to change the sign. This is the reduction one, 2 to 0. All right, when we add these up, do we get a positive or negative? Positive. So will this displacement happen? Yes, it's thermodynamically favored. Okay, so in these next two problems, we're actually going to find the exact voltage. We don't have to predict the equation, but this is no harder than what we just did, except we're actually going to add them this time and get that voltage. So we have a redox equation. The process of this, they also want us to balance the equations in acidic solutions. So we're going to go ahead and do that as well. Y'all want to start with lead or chlorine? I don't care. Lead. How do I balance that? 2 electrons. And then chlorine is Cl2 going to Cl minus. How do I balance that? Yes, balance everything but H's and O's first, so that means I have 2 electrons here. Always check your electrons. They have to be on opposite sides. If they're not, you mess something up. Now, let's go ahead before we balance. I always like to find the voltages first. I want you to see how if you balanced your half reactions correctly, you're going to find that exact half reaction on your sheet, or the reverse of it. So it's a good way to check, did I balance it right? Because if you can't find exactly what you balanced on there, you screwed up. So start looking them up, see what we can find. Positive or negative? Okay, this is 0.1251 negative on the table, but notice it's going up in charge, so this is oxidation. Therefore, I need to add it because it was the reverse. 1.358. So because of sig figs, we're going to round this to what? Addition of sig figs. 3 decimals, correct. So I can pretty much ignore this last guy. 5 plus 8 is what? 13, 8, 4, 1 volts. Okay? Now let's go ahead and balance it. That's a nice one. All we have to do is add them. It was originally balanced as it was. Oh, no, it wasn't. That 2Cl minus needed to be put in there. And that is now a balanced equation. Now, I know it says acidic solution. If it doesn't have H plus or OH minus in it, like this one, it's balanced in both. You don't need to do anything to it, both acidic and basic. It's neutral, so nobody cares. Okay? All right, last problem. This one's going to be an ugly one to balance. But let's do it. What do you want to start with? The Mn or the Cr? Mn. So Mn plus 2 goes to MnO4 minus. Balance everything but H's and O's. Done. Balance O's using water. How many what side? Balance H using H pluses. Okay, we have an overall of plus 2 on the left. We have an overall of plus 7 on the right. What do I need to do? Do what? 5 on the right. And that is now balanced. Okay, let's go to the next one, the dichromate. Let me move over a little more because this is going to take up a lot of space. All right, balance everything but H's and O's. 2 CRs. Don't let that trick you. Plus 7 waters on the right. How many H pluses? 14 H plus. So we've got a plus 12 on the left and a plus 6 on the right. So I need 6 electrons there, correct? Now let's do voltages before we add these up because we're going to start making them look ugly. And I want you to pay special attention how that complex balancing we just did, you're going to find that exact equation on your table. So everyone look at the reduction equation is this one. You're going to find this exact equation on the table exactly as it is. As it is on there? It's positive on the table. 1.36. But do y'all see how down to the electron it's exactly the same? Use that to help you balance if you screw up your balancing. Okay? Now, let's go back to this. Caroline was saying it was positive 1.51 on the table, but that was the reverse of it. So we need to make this negative. So what is that? I know it's negative something. 36, 37, 39, 15. All right. I used my fingers on that one on my leg. I was like, 40. All right. So now we can go ahead. This is a non-spontaneous reaction. This is not thermodynamically favored, so it's not going to happen. It's not going to make a good battery. In order for us to add these up, I have to multiply the top by 6. Let's do that first. 24, 6, 6. 6 times 8 is 48, 30. Okay, the bottom we multiply by 5. 30. Is that 70? 5, 10, 35. I know. This is why these get kind of crazy. And so now we're going to go ahead and clean house. So what automatically goes away? Let's get rid of those out of our site because they're 30 and they're 30. I can clean house. Waters? How many? I need to get rid of 24. How many does that leave on the right? 11? 11. And then I'm going to get rid of H pluses. I've got 70 on the left and 48 on the right. 22? 22. Oh, let's get rid of the whole thing. 22. So let's just rewrite this because it's an absolute disaster. Do a spot check. When you have a balancing one that's this ugly, pick an element and ask yourself, is that balanced? Oh, my MNs are balanced. That's good. What is 10s? What was I doing there? Chromium. It's a 10 plus 3. Do we have 10 chromiums on the other side? Yep. And then the last thing I like to do is just check the overall charge. On this side, I've got, 22 plus 12 plus or minus 10. So is that 24, right? 24 on this side. I've got 30 minus 6, 24. So if you check that charge in something this complex and the charge is balanced like that, you know you're good. Okay? Always double check this because it would be silly to make a mistake on something like this when it's so easy to check your mistakes. Because not only do you have the ability to check your charge and stuff here, you also have your reduction potential tables that have the half reactions already written for you. Okay? You got lots of places to check for errors. All right, so this is not spontaneous either. Not going to happen. All right, so tomorrow we'll talk about batteries.